Well, it's good to be back at Lumini. Want to thank the organizers to give me possibility to speak here. And on this conference on, if I remember well, D modules, applications to algebraic geometry, arithmetic, and mirror symmetry. So from that scope of the conference, it's already clear that we all know that differential equations rule the world. And so it's well, there is a deep truth in it. Differential equations appear not only in algebraic geometry and the subject of this conference, but it has a much broader scope. But I want to add something to it. I want to write here Fuchs differential equations rule the world of motifs. So this is sort of the theme of the two talks I want to give. So I will be focusing on sort of arithmetic part of the theory of differential equations, which is a large subject of which I know only the beginnings, and it is related to the other two topics, algebraic geometry of varieties, of Calabial varieties, and mirror symmetry, which leads to interesting examples. And of these class of examples, I look at the arithmetic properties, and I find that these are determined by the differential equation. So that will be my story of today and Friday, and we'll try to highlight different aspects. Today I want to talk about some work I did with Philip Candelas and Xenia de la Osa, and on Friday I will speak on some more recent works I did with Vasily Golishev. So I think there should be no conference on such a subject without writing one differential equation, which I call number one, the most quintessential differential operator. It's a fourth order operator, and it is the one which started many developments in mirror symmetry, in enumerative geometry, Gromov-Witten theory, were all related to attempts to come to terms with the mysteries of this single differential operator. It's, from the standpoint of differential operators, it's just a fourth order differential equation of hypergeometric type. And it has a Frobenius basis of solutions. It is, by the way, quite remarkable how the name and the person of Frobenius has become attached to so many subjects which are of importance to our field. We had the talk on Frobenius manifolds, which exemplifies this very well. Frobenius basis of solutions near the origin. Well, we all know how it works. So there is one holomorphic solution which starts with 1, and you can give the power series expansion explicitly. It's this series, and then there is a solution phi 1 which starts with a logarithm of t plus further terms, and then there is a solution which starts with log squared and log cubed terms, and this causes this differential equation to have a point of maximal unipotent monodromy at the origin. So theta is my shorthand notation for the logarithmic derivative. So you have this fourth order equation with the fourth solutions. These other solutions are defined only on a slit plane. They contain the logarithms. The monodromy is a Jordan block of maximal size, and this is the mum point. Well, this remarkable operator knows a lot, knows everything about two different Calabial manifolds. So this is L, maybe here. L knows almost anything about the enumerative geometry of the quintic in P4. And in particular, it's instanton numbers. The number of lines on the quintic, the number of conics on the quintic, the number of twisted cubics. Now I forgot how many there were. What was it? I think it was this large number. And of course, this is what made this operator famous in the paper by Candelas, Van Ossa, Parks and Green in 91, that this operator rules the enumerative geometry of the quintic. And well, I will not go into the details of how to obtain these numbers from this operator, although it's a very simple algorithm. You go to the so-called q coordinate, write the operator in the q coordinate, and then in the normal form for that operator, you find the Yukawa coupling, and then you read off these numbers. This is by now very well known. And in the same paper, we know that this L is a Picard-Fuchs equation, so it also appears from the mirror quintic. L knows almost of anything, everything about the mirror quintic. So the mirror quintic, it's a family over P1. So it's a one-parameter family of Calabial manifolds. And they fit in a family over P1 minus the three singular points of this operator, the three singularities. And so this is the fiber at T. And then we have a third cohomology group. This is a four-dimensional. And so this is a Calabial manifold. There is a holomorphic 3 form, and the periods are the integrals of the 3 form. So omega 3 form over, I'll call this S. So we have a family of 3 forms, and you can calculate this over cycles, homology cycles, integral homology cycles. So this is a period function. And these periods are all satisfy the same differential equation, so it can be expressed in these special period functions. So, of course, this cohomology group has many structures. So, first of all, it's a Hodge structure. Hodge structure. With Hodge numbers 1, 1, 1. 1, the fact that you have such a mum point and a variation of Hodge structures forces, in fact, this Hodge structure to be of this type. So all Hodge numbers are 1. And this family of varieties, this is the mirror Quintic family. You can write it down in equations, and the equations are defined over Z. And you can also look at XTP is XT mod P. So we take the equations of the Quintic mirror and reduce mod a prime number P prime. And for many things, which for all things I will explain today, there will be always exceptional primes to which we have to exclude. And this, for this specific example, the prime 5 is, of course, notorious. This is appearing everywhere. This is a prime of bad reduction for all the fibers in this family. So we want to exclude that. But any, but assume that T and P are such that this is smooth. So for such smooth, we have a nice smooth variety over FP. And you can ask about further cohomology groups. You can look at the crystalline cohomology or étale cohomology groups. And, well, we will be sort of modest, so we will maybe ask about the number of points. So, just the number of points. So this is the same as the number of points of the scheme with coordinates in FP. Or we can look at the Frobenius, another Frobenius. How to write Frobenius? The Frobenius endomorphism on the cohomology, so there's the Frobenius at the prime P, and also at the value T. And then you have the characteristic polynomial, so let's call this just briefly F. F will be the Frobenius map transformation, and via the Weil conjectures, the counting of points can be expressed in the action of the Frobenius on the, any Weil homology. So you may think of this crystalline homology or étale homology. But the point is, so then you have the Frobenius polynomial P is the determinant of I1 minus t times the Frobenius. This is a polynomial of degree 4 because it acts on a four-dimensional group. This is can be represented as a 4 cross 4 matrix. You take its determinant, so this is a polynomial of degree 4, and it will be of this shape. T6 T4. So this is the characteristic polynomial of the Frobenius. So this is a polynomial of degree 4 with coefficients in an additional eigenvalue parameter t. The roots of this polynomial are have the size. Reciprocal roots have the size p to the power 3 over 2 by the Weil conjectures, because we're dealing with a weight 3 motif. So this is a weight 3 motif. So what I want to stress and at this point is that this differential operator L knows anything about the mirror quintic. It knows, of course, the Hodge structure because it knows the period. We know all the periods, and knowing all the periods, I've written them down. It determines the Hodge structure for each of these four-dimensional spaces. But there is sort of a p-adic analog, and now the claim is L also determines the Frobenius F and its characteristic polynomial, and thus P. So the differential equation, the Picard differential equation, rules the world of the motifs. It tells you what the motif is. So it is information which is not classically attached to a differential equation. This differential equation answers us very precise arithmetical information about a specific variety. So this is maybe unexpected to those who are not used to work at these things, but I think this is a very remarkable fact. And the point of the talk was, of course, that so this is work with so this is now work with Candelas de la Osa and myself, where we, for the quintic, there are earlier papers by Candelas about the number of points of the mirror quintic, but our discovery is that there is a universal expression for the Frobenius matrix, which holds for any differential equation similar to this one. So it can be applied to all differential equations coming from one parameter families of Calabial manifolds with such Hodge numbers 1, 1, 1, 1. And even if the dimension is higher, you have more ones. This is what I call Calabial motifs. So these are motifs where all the Hodge numbers are 1, just a string of ones. For those appearing near a mum point, there is a universal formula for the Frobenius. And this is remarkable, and this is a so it can be seen as periodic gamma conjecture. So the gamma conjecture was mentioned in the previous talk in relation to Frobenius manifolds, and the characteristic class which appears there, where you use the gamma function as characteristic, as determining a new characteristic class for varieties. And now what we turns out we use the p-adic gamma function. So we see that those differential equations which appear in such a way, which are usually for the Hodge theory and the complex analytic world, the gamma conjectures are important, but if you go to the p-adic world, you have similarly that the p-adic gamma function crops up. So this is sort of the theme, and now I see I already spend a lot of time. So let me these were the introductory words. So in order to understand these things, it is maybe good to go to the very simplest example where you have such a differential equation determining the arithmetic of a variety. So and this is the Legendre differential equation, which you probably all know very well. We have a family of elliptic curves given by this equation. And T is a parameter running over P1, and there are singularities 0, 1, and infinity. This is also will give a hypergeometric family, a period, a holomorphic period. Well, the period function will be integral over a cycle on this Riemann surface of the holomorphic differential form, suitably normalized, so it is 2 times 0, 2. This is just the period of the Legendre differential equation, and if you expand this in a series and compute, you will find the following. Nice series. Well, what? One term more, like this. which can be also written as 2 pi sum 2n over n factorial t over 16 to the power n. So this is a nice series 2f hypergeometric series, and well, clearly our operator L is a sort of similar. So let's look at the history of this thing. So we have this period integral, and now let's look at the number of points of this curve mod p. So well, if you think about the number of points on an elliptic curve, there is, first of all, there is the famous theorem by Hasse saying that if it's any elliptic curve, then can be written in this form. There is a coefficient, the number of points is 1 plus p minus ap, where ap is a irrational, erratic term, depending in an unpredictable way on the elliptic curve. And this ap can be interpreted as the trace of a Frobenius acting on the first homology, which in this case you can maybe take as the Tate module of your elliptic curve. And so this is the way. And Hasse's theorem is that the size of this trace cannot be exceed 2 times square root of p. So this is a property. Then can I write here? Yeah. So this is I forgot to say, this function, of course, is a solution to the Legendre differential equation, which is now this second order equation. So this satisfies the second order equation, and this is the, up to this factor 2 pi, it is sort of the normalized holomorphic solution. And so the number of, we have this inequality, and then there is the question how to determine this AP. So in fact there are formulas for specific elliptic curves for this AP already in the work of Gauss. But then there was a nice formula by Deuring, the German mathematician Deuring, which is saying that for and one has AP T if ET mod P is smooth, then the number of points, so this is just the AP of EP, and it is exactly the same solution. So what you have, this is now a polynomial in T. So you take these binomial coefficients and then this and take a sum of the first p terms of the same series as there. And then you have to multiply it by a sign. And this is an equality mod p. Yeah. So if we take that equation and reduce it mod p, then everything is mod p. The t is also a variable in fp. Say, but now you can substitute for t anything. This is a polynomial, and it gives you the number of points on the elliptic curve mod p. But now look, this AP is of the size square root of p. If p is bigger than 5, then there is just a unique number AP, which is smaller than this, which is mod p equal to that number. So this determines with Hasse so p is not, of course, p cannot be 2 here, right? Because we divide by 2. Yeah? P is not 2. There are usually exceptional primes which have to be avoided. I will not be able to say this at every point in this talk. So it's very remarkable, and at that point, I think, unexplained, why the Hasse polynomial, which this polynomial is called, if this function, and they were mostly interested where this is 0 mod p. These are called the supersingular curves. And then there was a work by Iguza. So this was 1941. But this is a very long history. (1958). Iguza remarked that APT is congruent to this series. So without the 2 pi, call that phi of t. Meaning that, well, we truncated here at step p, but we could have continued the series. But all the terms in the series with higher exponents of t, they're divisible by p anyway. So I can just take the complete series. So Iguza remarks that the solution to the Legendre differential equation taken mod p is the Frobenius trace. Just equal mod p, which is a very remarkable thing. And he used this to conclude that the Hasse polynomial has distinct roots. The roots cannot coalesce because they satisfy this differential equation. So he made use of the differential equation to give an arithmetic application. Then this was the starting point for Dvorak. And this is the early 60s, maybe 62, where if we look at this polynomial So this is the polynomial determinant. Frobenius. The Frobenius acting on the h1 of the elliptic curve. Well, this in general, these coefficients, this is a polynomial with integral coefficients. But now what Dwork supposes to do is to factor this as a product of its two roots, to factor it in as a p-adic polynomial. And there will be one root, which is a p-adic unit, and the other one will then necessarily be p divided by u. There will be such a unit root if this number is non-zero. If the Hasse polynomial vanishes, then we have supersingular, then there is no unit root. But if there is a unit root, you have a formula for the unit root, and this is u. Well, it depends of course on p and on the point t. It's a p-adic number which is determined by a t in fp. And what it is, you take the phi so take the period function and divide it by the period function of the argument where you replace xi by xi to the power p, and then let go xi to the Teichmuller lift of t in fp. So if you have any number in fp, it's a number mod p, but you have to lift to a p-adic number which has as a residue this t. And there is a unique way to do it called the Teichmuller lift, which has the property that the p power of this number is equal to t tilde itself. So this is the Teichmuller lift. It's very easy to compute, but this gives a way to go back from mod p to real characteristic zero. You go back from characteristic zero to characteristic p to characteristic zero. Because AP is an integer, not an integer mod p. How to get the integer? Well, you compute up and add to it p divided by u. This gives an integer AP. So this is the way Dwork gave his famous unit root formula for the coefficient AP. I give it here for historical reasons because there are better formulas. But I also want to give it because what I'm going to explain is best understood as a generalization of this. So let's go on. So the question is how to, yeah. I do it the French way. So, because I'm Dutch, so. So the interesting thing is that the differential equation, well, this of course is a very special differential equation. So people started thinking about what makes this differential equation so special. And then you get the theory of differential equations of geometrical origin, or Picard-Fuchs equations. So there was the work by Katz, and then you have the notion of global nilpotence, and the theorem of Katz and Honda on the fact that if you have a globally nilpotent operator, then it is regular singular, and all the exponents are rational, all the things we expect. It's also a G function, a G operator. It has a solution which has bounded denominators. So here, the denominators were bounded by 2 to the power n. So the denominators of the solution do not increase too quickly. In contradistinction to the exponential function, where you have a factorial in the denominator, here it's geometrical growth of the denominator. This is the theory of G functions. These are all things of general nature and became important building blocks in arithmetic geometry. What I want to tell is a specific formula, sort of generalizing this work formula, which applies to, in particular, to the examples of Calabial manifolds like number 1, which is erased just, and similar operators. So what about how at higher dimensions? Analog. High dimensional cases. Well, of course, after elliptic curves, you have Calabial manifolds of dimension 2, which are K3 surfaces. I leave them out because they're still in the realm of classical algebraic geometry. But if you go to Calabial threefolds, you have these four-dimensional motifs, which are mysterious. The Hodge structures are mysterious, and the arithmetical properties are mysterious. So we go to three-dimensional Calabial threefolds, and how to get interesting examples of. We have this success story of the quintic and the mirror quintic, how to generalize it. And there have been many attempts. So we, after this mirror symmetry was discovered, it was immediately extended to toric mirror symmetry by Victor Batirev. And then one of my fondest memories was with Boomzig Kim was the encounter we had in Mittag Leveler in 1996, where we decided to try to do mirror symmetry for non-toric. And in particular, we wanted to look at Calabials, say, in other Fano manifolds. Is that Fano? And the simplest Fanos that are not of toric type and which were easy to study is the Grassmannians, Grassmannian GKN. And what we did, so this is a Batirev, Sirkan, Fontanin, Boomzig Kim, and myself in long ago. We looked for complete intersections in Grassmannians. And the quantum homology of the Grassmannian was known, so we can compute the quantum differential equation for the Grassmannian. So if you do for P4, you get this for the small quantum homology ring. We cannot do the. If you do for P4, you get this operator, and then there is a solution So this is the quantum differential operator belonging to P4. It has a solution which is this one. This is irregular, of course. And then you can make a Laplace transformation or a convolution with an exponential object and change it into 5n factorial, which brings you to number 1. So this is a regularization or Laplace transform. As I say, just a regularization. The quantum differential equation for G25, which we computed at that time. G25 is a nice 6-dimensional manifold, and the cohomology is 10-dimensional. So it's a differential operator of order 10, and I do not know it by heart. The operator reads as follows. It's of course also irregular. It's interesting that you can read off immediately the classical cohomology from this operator, the sort of, because the Betti numbers of the G25 are 1, 2, 2, 1, 1. So this is 1, 2, 3, 4, 5, 6, 7 steps. This gives this. And there is theta minus 1 to the cube. These are these 3 extra things here. So this operator reflects already the classical cohomology, and it's a very nice thing. It is not hypergeometric, so these were the first non-hypergeometric cases. And the solution looks like the following. So there is here an extra coefficient an, and we computed this. You see there is a rapid increase in the denominator, but it's just a simple factorial. And in fact, you can give a closed formula for an, and we found the formula as a binomial sum. And we, in fact, find a similar formula for all GKN. And I still have in my possession a small slip of paper saying, "Dear Mr. van Straten, we found the solution, hypergeometric series." So this was written by Ionut and Boomsich Kim when they came up with a general formula for the series, and they called it the hypergeometric series, although it's of course not hypergeometric in our sense, but it's the analogous of the hypergeometric series. But this coefficient here for this G25 is in fact nothing. This is the famous a priori numbers. So we were surprised to see that the analysis of the Grassmannium brought out already some interesting relation to the a priori numbers. And now this is an irregular operator, but you can do a similar regularization or convolution by exponential objects. In the category of D modules, it's just a convolution with an exponential object. Here, it would be 5n factorial. So it's a Hadamard product to make from here to here. And if you do this is a complete intersection with hypersurfaces of degree this Grassmannian, the G25, has a Plugger embedding in P9. The 10 minors of a 2×5 matrix gives the embedding of the G25 in 9. In fact, here it's a Pfaffian given by linear equations, quadratic equations, which are Pfaffians. Very well studied the projective geometry around this thing. And now I take in P9 intersections with things. And then you can regularize. Now assume that D1 plus D2, the sum is 5. Then you can look at the series so like this. And this is now satisfies a regular singular differential operator. So if you take D1 all ones, then the factorial is just ignored and you get the series an Tn. And this is the famous a priori differential equation. So now it satisfies differential equation solution to this second order equation.
Calabial.
Yeah, well, to get this to regular singular. Yeah. You need, of course, that the asymptotic that to make it regular singular, then you have that condition. That's of course a Calabial condition. Indeed, if you take the Grassmannian and take 5 linear sections of your 6-fold, you end up with an elliptic curve. And the mirror of the elliptic curve has this Picard-Fuchs equation. I will talk about that case on Friday a little more, because there is a nice story there as well. But what we were interested in getting 3-folds, so we take 1, 2, 2. And then you get 2n factorial squared divided by n factorial. Yeah? So this is this solution to the this is the period of a mirror for the this is a Calabial 3-fold in the Grassmannian, and you have this differential equation And if you do the differential equation it satisfies is maybe I'm running out of time. It's good that I have another talk on Friday. Then. Yes, yes. So let me write that down. So for y1, 2, 2, we get as a regularized differential equation this one. So this is an operator that ended up as number 25 in the list of Calabial operators. And it is a genuine new operator. So there are now 4 singular points. I draw the Riemann symbol. The origin is a mum point. Then there are 2 points where the exponents are 1, 1, 2. So this is a conifold point. And then you can see the exponents at infinity are a half-half. So at infinity we get 2 Jordan blocks. At these 2 points there is a single Jordan block of size 2, and here is a Jordan block of size 4. So this is a non-hypergeometric operator, but if you do the yoga to get the instanton numbers, you get indeed the right instanton numbers for this Calabial manifold. And for this operator, we managed to construct a mirror family with Hodge numbers 1, 1, 1, 1. So it's a complicated Laurent polynomial. I will not write it down. And it defines over P1 minus these 4 points a variation of Hodge structures. These 2 points depend on square root of 5. You get a nice family of Calabial threefolds with Hodge numbers 1, 1, 1, 1. And it's not hypergeometric, and so it was not clear how to get the motifs of these fibers of this family, as can be done for the hypergeometric cases. Now I have 50 minutes left. I will give you a universal solution how, with the input of such an operator, L, you can associate a matrix which conjecturally has always the right properties, and in examples gives us exactly what we expect. So this is the ultimate generalization of what I explained first about the elliptic curve, which determines its number of points. So I will now hurry up to do this. So this is part 3. Construction of a crystal. So after Dwork, there was a development of crystalline comology and crystals. which is basically a differential equation which and a Frobenius map which act compatibly. And our input will be a differential operator. It can be of any order. D is the dimension of the... I imagine that it comes from a variation of d-dimensional varieties. And so this is I will assume that the coefficients are integral or rational. You can always... That's a differential operator. Delta t determines the singularities. So it's the symbol or the leading term. So the roots of this will be the singularities. And I will assume 0 is a point, is a mum point. So we can also write L up to multiplication by something is t times. Like we have written here, it starts with theta to the power 4, but it can start with any power, and then it means that 0 is a mum point with all exponents equal to 0. Yeah. So this is a very important problem. But there are the conjectures that if you have an operator where the p curvature is nilpotent for all p, then it should be a Picard-Fuchs operator. You can check this for small p. Or you can look at a differential operator and look at the solution. Look at the denominator. If the denominators grow and you get strange primes to high powers coming up, forget it. But if the denominators are behaving nicely, for example, if you have an integral solution, if you have a differential equation with an integral solution, and here we have such a thing, almost by construction, we have an integral solution. If you have an irreducible differential operator with an integral solution, then it should come from geometry. It should be already Picard-Fuchs equation. So, although all these things are unproven, as a heuristic principle, they have turned to be very useful. So you can quickly, on a practical level, decide which differential operators are good to look at and which are not good. Of course, if you look at the one with the factorials, the exponential function, you might say first, well, it satisfies an irregular equation. It can never be a Picard-Fuchs equation. So to be sure, you make convolution with exponentials or to remove the factorials to see whether it gets better. And so this is the way you can practically. Yes. That's another very good thing. If you just have the differential operator and the solution as a series, then you're not so good shape. But if you have a formula for the solution, like here, then in fact, there is an algorithm to write down the equation. Maybe I tell on Friday. You see, if you have a binomial, then you can represent it as a diagonal. This is slightly more general than Laurent polynomial. So you can, in a way, these formulas like this is a good formula. If you see this formula, you know there is a variety. Now, at the time when it was discovered, it was not clear, but now it is. Now the smoke is I'm getting input. We have such an operator, and the output will be a matrix F a matrix now for all good primes P, there will be something which will be the Frobenius at P depending on the parameter T, but I construct this Ft and it will be a series in Q. It will be a matrix of size such that the determinant of I1 minus Ft T will be the determinant of will be the characteristic polynomial of Frobenius for a family whose Picard-Fuchs equation is this. So this is something you can do without having that family. So you can say it is the Frobenius operator which belongs to this differential equation. So you can, in a way, forget about the operator. And the remarkable thing is that if you look at the eigenvalues of that matrix for various values of t, they satisfy the while bound. So they have the right size. They have the right weight in all the examples. So I'm getting a little bit... so I will have to write down the formula. I'm getting a little bit in time. So this is the p-adic gamma conjecture. You can motivate it a long way, but I will just give the formula. So we let E is this is a matrix. This is the fundamental matrix of solutions. For the operator L. So this is a matrix which has its first column this Frobenius basis of solutions at the mum point. And then you apply theta to it, this logarithmic derivative. So you get a square matrix. This is, or the Vronsky matrix, or the fundamental solution matrix. So remember that phi 1, and here there will be logarithms appearing. And now I take a matrix F0, which is the putative Frobenius matrix at the mum point. And from that, I construct Ft is so if you take this was the discovery by work that if you know the Frobenius matrix at one point, the differential equation tells you what it will be at another point. What we do is very cavalier. We take this most singular point, and there you cannot really interpret it as the Frobenius matrix of that singular variety. But on the other hand, we can give a precise guess for this F0 is lambda. So there is a lambda is a diagonal matrix with all powers of p. So it's a d plus 1 cross d plus 1 matrix. For a one-dimensional thing, you get a 2 cross 2 matrix. For the Calabial threefold, you get a 4 cross 4 matrix. The d is the order of the so the size is d plus is 1 bigger than the dimension. So, and what is the gamma p? Gamma p. So this is the p-adic gamma class. So it is the product of the Chern roots, and I take the Morita gamma function at the prime p and substitute in it the Chern roots and multiply it by the matrix n. So lambda e is the Chern roots. This and n is the logarithm of the monodromy at the origin. This is a fundamental, is a nilpotent element. So this is the Jordan block. Of the tangent bundle of x. So if you start with a y, sorry. If you start, so in the generality of if you're just a differential operator, you're left with an ambiguity. But if it arises as the mirror variation of a Calabial y, then you can exactly say this. Otherwise, it is well, yeah, but almost. I put almost, and then another almost is this sign. You may remember that in the example with the Legendre differential equation, there was the sign minus 1 to the power p minus 1 over 2. This is a sign ambiguity you can never get rid of. But I can I agree this is maybe not properly. Okay, let's restrict for d is 3. This matrix F0 looks as follows. And now, if you start with a Calabial and compute this gamma class, then you will still get that there are zeros here. And here there is a number. And this is, and gamma is a rational multiple times periodic gamma 3. And the rational number is the third Chern class of y divided by the degree of y. But this is if the operator arises in that way. But the remarkable thing is that with this choice of this entry here, this function here gets arithmetic meaning. Then you will find that the eigenvalues have the right size for one specific choice of this rational number. And then in the case of mirror symmetry, this rational number is predicted to be this value. Or put it in another way, if you have a Fano manifold, then this is the only number which sort of not given by the differential equation. Although if you can experimentally find the number, because there will be only one number, R, for which this matrix you get has a good property. As a good property is that if you look at that matrix, it's a matrix of p-adic numbers. No, with rational numbers. But if you compute mod p to the power n, it turns out to be a rational function where the degree in T and and En depend linearly on N and P. So the main point is if you compute this series with any f0 and you reduce it mod p to the power n, you get, so you expand it to 1,000 terms. You reduce mod p to the fifth. Then you still get a series of 1,000 terms. But for one specific value of r, you will see that it collapses to a very, very small polynomial. And it is exactly this value in the examples we have. We have such a case. So this is, I think, a great discovery, because this enables us now to compute without using the equations. You can compute the number of points on the variety which we discovered with Boomsinghin. And well, I'm getting over time, so I'm sorry for going over time and making a mess of it. But okay, well, let's stop here. Yeah.